Welcome back to Timekeepers for Sleep. If your day has been running on deadlines, meetings, and notifications, if your mind still feels like a wall of blinking status lights that refuses to dim, if you've spent hours chasing seconds, watching clocks, wondering where time goes, tonight you don't need another productivity hack. You need a story that's precise enough to satisfy your curiosity and gentle enough to let your thoughts drift off without a fight. This is a long, quiet sleep story about atomic clocks. The machines that keep time for the entire planet. The devices that forced us to rewrite what 1 second even means. No math test. No technical exam. No pressure to remember any numbers, any formulas, any dates. You don't have to stay awake until the end. You don't even have to make it past the middle. You don't have to make it past the next 10 minutes. You can simply lie there, let your body become heavier with each breath, and let this slow story hum away in the background, like the faint, steady tone of an atomic clock in a distant lab, counting seconds you no longer need to count. If on some other night you decide you'd like another story like this, you'll know where to find us. We'll be here in this same quiet space with more stories about time and the people who measure it. For now, make yourself comfortable. Adjust your pillow if you need to. Pull the blanket a little higher, or push it down if you're too warm. Find the position where your body can rest without needing to shift again for a long while. Let your shoulders fall where they want to fall. Let your hands rest where they land naturally, palms up or palms down, curled or open. It doesn't matter. There is nothing important you need to hold. Nothing you need to grip. Nothing you need to keep track of. Take a slow breath in through your nose and let it drift out through your mouth in your own time at your own pace. Begin. And out. One more time. And out. Good. Tonight, we'll start in a quiet hallway inside a time laboratory where the air is cool and the lights are soft. We'll walk backward through history from sundials to cesium atoms, from the sun's shadow to quantum transitions. We'll step inside an atomic clock itself, see how lasers cool atoms to near absolute zero, watch how microwaves interrogate their natural frequency. And then we'll come back to this simple reality. While these machines are keeping the world in sync, measuring time to 19 decimal places, you are allowed to sleep. You are allowed to let time pass without measuring it, without tracking it, without wondering where it went or where it's going. You are allowed to drift. The atomic clocks will keep counting. They don't need your help. Imagine a large building on the edge of a city. Not downtown, where glass towers reflect sunset light and traffic moves in waves. But at the outskirts, where research campuses spread across open land, where buildings have numbers instead of names, where parking lots are half empty even during business hours. During the day, this building is full of scientists, engineers, postdoctoral researchers, visiting delegations from other countries. Students on tours, journalists with cameras, technicians calibrating equipment, programmers writing code to analyze data. At night, the parking lot is mostly empty. A few cars belonging to technicians on evening shifts, their windshields collecting dew. Security lights casting long shadows across concrete marked with painted lines that have faded from years of weather. The main entrance is locked, but a side door remains accessible for authorized personnel. Inside, most of the building is dark. Conference rooms empty, desks vacant, coffee makers switched off. But lights are still on in certain interior rooms. Rooms with no windows, rooms where equipment runs 24 hours a day, rooms where time itself is being generated. You walk down a long corridor. The floor is polished linoleum, institutional and clean, softly reflecting the overhead fluorescent lights that never turn off. Your footsteps make a quiet sound that seems to travel far in the stillness, echoing slightly off the walls. The air smells faintly of electronics, of carpet cleaner, of coffee from earlier in the day. On the walls, there are framed photos documenting the history of timekeeping at this laboratory. Early pendulum clocks from the 1800s, with ornate wooden cases, brass weights hanging on chains, faces painted with Roman numerals. Black and white pictures from the 1950s showing men in white lab coats, thin black ties, horn-rimmed glasses, standing next to strange metal racks filled with vacuum tubes, dials with needles, switches labeled in careful handwriting. Color images from the 1980s and 90s showing the evolution toward modern equipment. Digital displays replacing analog meters, computer monitors appearing alongside oscilloscopes, cables becoming more organized. More recent photos showing ultra-modern apparatus, tall vacuum chambers wrapped in magnetic shielding, laser housings bristling with adjustment screws, optical tables covered with mirrors and beam splitters arranged in precise geometric patterns. At the end of the hallway, you come to a heavy door. It's made of steel, painted an institutional beige with a small badge reader mounted on the wall beside it. A green LED indicates the system is active. In our story, you have access. You present your badge, not because you need to in reality, but because in this imagined tour, you're authorized to see what happens inside. The reader beeps softly. The light turns from red to green. An electromagnetic lock releases with a solid click. The door opens with a satisfying sound. a hermetic seal releasing, pressure equalizing, then the soft hiss of climate-controlled air meeting the corridor's warmer atmosphere. Inside is one of the places where official time is generated. A national metrology lab. One node in a global network of institutions responsible for keeping the world's clock synchronized. The quiet heart of an entire country's timekeeping infrastructure. The room is cool. Not cold, but noticeably cooler than the hallway, kept at a stable temperature, perhaps 20 degrees Celsius, controlled to within 1/10 of a degree. The air feels still, almost motionless, as if even the atmosphere has been asked to be stable, predictable, reliable. The lighting is different from the harsh fluorescence in the corridor. Here, the illumination comes from concentrated pools of light above each rack of equipment, leaving the upper regions of the room in soft shadow. The overall effect is calm, professional, purposeful. Everywhere you look, there are instruments. Tall equipment racks line the walls, standard 19-inch racks like you'd find in any server room, but filled not with computers but with specialized electronics. Their front panels show LED indicators, some green, some amber, one or two blinking slowly in a regular rhythm. Labels on the racks: microwave synthesizer 2, hydrogen maser reference, frequency distribution amplifier, GPS disciplined oscillator. Thick cables connect one system to another, bundled neatly with Velcro straps and labeled with small plastic tags marked in laser-printed text. Computer monitors display graphs of frequency stability over time, lines so straight they barely change from hour to hour, day to day. In the middle of the room, surrounded by additional shielding, sits the main apparatus. A stainless steel structure, perhaps 2 meters tall. A vacuum chamber. Cylindrical in shape, with thick walls designed to hold nothing, pure emptiness inside, pressure lower than outer space. Small circular windows, viewports made of special optical glass, allow you to see inside. Through them, you can detect a faint glow, the residual light from laser beams being scattered by atoms. Pipes and cables loop in and out of the chamber, some carrying coolant, some carrying electrical signals, some evacuating any stray molecules that might leak into the vacuum. Vacuum pumps sit nearby, running continuously, maintaining the emptiness inside with a low, barely audible hum. Inside that chamber is not a pendulum, not a spring, not a gear, not a wheel or weight or escapement. Inside that chamber are atoms. Tiny clouds of cesium, cooled to temperatures just millionths of a degree above absolute zero, being nudged by precisely tuned laser beams and interrogated by carefully controlled microwave fields so that they reveal their natural rhythm, the frequency at which their internal quantum states oscillate. You are standing in front of an atomic clock. One of perhaps 20 such devices operating in the world at this level of precision. Your phone's clock, when it syncs to network time, is drawing ultimately from systems like this. Your computer, your car's navigation, the timestamps on financial transactions. All of them, somewhere in their chain of synchronization, take their time from machines like this one. You don't have to understand how it works to benefit from it. You don't have to keep up with the technical details. You just have to listen, to rest, to let the story unfold. The room is remarkably quiet. There's a low hum from cooling fans inside the equipment racks, barely audible, like a distant engine running somewhere far below. A very faint electrical buzz from power supplies, the kind of sound you stop hearing after a few seconds, the kind your ears automatically filter out. But no ticking. No chiming. No mechanical sounds at all. The temperature is held constant to within small fractions of a degree. Humidity is controlled by dehumidifiers that run silently in adjacent rooms. Vibrations are minimized. The building itself sits on special foundations designed to isolate it from traffic, from trains, from the rumble of the city miles away. Everything about this space is designed to reduce interference, to eliminate noise, to create the most stable environment possible for measuring time. Near one wall, you see another equipment rack labeled Hydrogen Maser 3 Reference. Next to it, Cesium Fountain 2 Primary Standard. Further along, Optical Clock Test Bed Strontium Lattice. Each one is a different approach to the same fundamental question: how long is a second? Each one represents decades of research, millions of dollars in development, the accumulated expertise of physicists and engineers from around the world. On a desk in the corner, almost as an afterthought, sits a simple digital clock. The kind you might see in a kitchen with red LED numbers. It reads the current time, accurate to the millisecond, updating smoothly 60 times per second. That ordinary clock, something you could buy for $20, is taking its time from the extraordinary systems behind you. To a casual visitor, it would look unremarkable. But to you now, it becomes a small symbol of how ordinary life rides on extraordinary precision. You notice a clipboard hanging on the wall near the door. On it, a printed checklist with boxes to be marked, entries to be logged, written in neat handwriting by whoever was here last. 1800 hours, check laser power levels. Cooling 40 milliwatts, detection 2 milliwatts. 1800 hours, verify vacuum pressure. Main chamber 2.3 times 10 to the power of -8 torr. 1800 hours, confirm microwave amplitude. -12 dBm into cavity. 1800 hours, log comparison to reference maser. Offset plus 0.21 times 10 to the power of -15. Every hour, someone makes rounds, noting readings, checking that everything remains within normal parameters. Most of the time, nothing dramatic happens. The numbers stay stable, predictable, boring. The graphs drift slowly, always within their expected ranges, never showing sudden jumps or unexplained variations. The atomic clock is designed to be boring. That, in this job, in this room, in this field of research, is the highest compliment you can give. Boring means reliable. Boring means predictable. Boring means nothing has gone wrong. Boring means the world's timekeeping infrastructure, the GPS satellites, the telecommunications networks, the power grids, the financial markets, can trust this machine to do its job without drama, without surprises, without failure. You take a slow breath, pulling in the cool, clean air of the lab. It tastes slightly metallic, carrying the faint scent of electronics, of metal, of the ozone-like smell that sometimes comes from high-voltage equipment. This is where we begin our story. In this quiet room where seconds are born. To understand why this machine exists, why scientists spend careers building devices to measure something as simple as 1 second, we need to step backward in time. Far backward, to a time before laboratories, before electricity, before mechanical clocks, before anyone thought of time as something that could be measured precisely. For most of human history, we measured time by things we could see with our own eyes. First and most obvious, the Sunday. People marked midday by watching shadows. When the sun reached its highest point in the sky, shadows were shortest. Before midday, shadows pointed west. After midday, they pointed east. They built sundials, simple devices, elegant in their minimalism. A flat plate marked with lines. A pointer called a gnomon, casting a shadow whose position told the hour. The oldest known sundial dates back to about 1500 BC, found in Egypt, carved from a single piece of stone. A sundial requires no moving parts, no power source, no maintenance beyond occasionally cleaning dust off its surface. Just geometry and light. It was good enough for organizing a day's work. Good enough to know when to meet someone, when to expect a meal, when to begin evening prayers, when to close the market. But sundials only worked on clear days. When clouds covered the sun, when rain fell, when fog rolled in from the sea, time became vague again, unmeasurable. And of course, sundials only worked during daylight. At night, you had to estimate time by the stars, by the moon's position, by how tired you felt. So humans developed other methods. Water clocks, where liquid dripped at a steady rate from one container to another. Candles marked with lines, burning down at a predictable speed. Hourglasses filled with sand that flowed through a narrow opening. These were improvements, but still crude. Temperature affected how fast water dripped. Humidity affected how candles burned. The quality of sand affected how smoothly it flowed through glass. Then, around the 1300s, came the first mechanical clocks. Medieval clockmakers, artisans, inventors, tinkerers, developed devices based on falling weights. A heavy stone or metal weight was attached to a rope or chain. Gravity pulled the weight downward. But instead of letting it fall freely, the rope was wound around a cylinder connected to gears. Lots of gears carefully cut from brass or iron. These gears slowed the descent of the weight from seconds to minutes to hours. An escapement mechanism, the heart of any mechanical clock, let the gears advance one tiny step at a time, producing that characteristic tick-tock sound we associate with clocks. The earliest mechanical clocks were massive. Built into church towers, cathedral belfries, town hall buildings. Visible and audible to an entire community. They rang bells on the hour, calling people to work, to worship, to rest. But they were noisy, temperamental, and crude by modern standards. They might gain or lose 15 minutes in a day, sometimes more. They required constant adjustment, constant winding, constant tinkering. Each clockmaker had their own design, their own compromises between accuracy and reliability. Clocks did not agree from town to town, even from building to building. But this didn't matter much. There was no railroad to catch that operated on a fixed schedule. No international meeting to coordinate across time zones. No telephone network requiring synchronized switching. Time was still local, still flexible, still approximate. Then, in 1656, everything changed. A Dutch scientist named Christian Huygens, building on theoretical work by Galileo, designed and built the first practical pendulum clock. The physics of a pendulum is beautifully simple. A weight suspended from a fixed point, free to swing back and forth. Gravity pulls it down. Momentum carries it forward. The combination produces a regular oscillation. The period of a pendulum, the time it takes to complete one full swing, depends almost entirely on its length, not on how far it swings or how heavy the weight is. Longer pendulum, slower swing. Shorter pendulum, faster swing. A pendulum 1 meter long at sea level swings with a period of almost exactly 2 seconds. Huygens connected a pendulum to a clock's gears through a clever escapement mechanism that gave the pendulum a tiny push with each swing, keeping it moving without damping its motion. The result was revolutionary. Pendulum clocks could keep time to within seconds per day instead of minutes per day. Suddenly, time became something you could actually rely on. something predictable, something measurable. For nearly 300 years, from the 1650s until the mid-1900s, pendulum clocks were the most accurate timekeepers humans had. You could wind a good pendulum clock on Monday morning, and by Friday evening it might be off by less than a minute. That was extraordinary precision for the era. Pendulum clocks spread everywhere. Into homes, offices, observatories, ships. Ships carried special pendulum clocks called marine chronometers, designed to work despite the rolling of waves, to help sailors navigate by comparing local time with time at a reference location. Knowing the time difference between your ship and Greenwich, England, for example, told you your longitude, your position east or west. This was literally life or death information for vessels crossing oceans. Observatories used pendulum clocks to track the motion of stars and planets with unprecedented accuracy. But pendulums had fundamental limits. They were affected by temperature. Metal expands when warm, contracts when cold, changing the pendulum's length by tiny amounts. A change of 1 millimeter in length would cause a clock to gain or lose about 40 seconds per day. They were affected by air pressure. Higher pressure meant more air resistance, slightly slowing the swing. They were affected by humidity. Moisture in the air changed its density. They were even affected by the tiniest variations in the strength of gravity from place to place. Mountains have slightly less gravity than sea level, changing how fast the pendulum swings. Clockmakers developed ingenious solutions. Temperature-compensated pendulums made from combinations of metals that expanded and contracted in opposite directions, canceling each other out. Clocks housed in airtight cases to eliminate air pressure changes. But there was a limit to how good a pendulum clock could be. The best pendulum clocks, at the peak of their development in the early 1900s, could keep time to within a few hundredths of a second per day. That sounds good. And for most purposes, it was. But science was advancing rapidly. Physicists were conducting experiments that required better timing. Radio broadcasting was beginning, requiring stations to coordinate their transmissions. Aviation was developing, with pilots needing to navigate precisely. Then, in the 1920s and 30s, came quartz crystals. Someone, actually several people working independently, discovered that if you cut a piece of quartz in just the right way and apply an alternating electric field to it, the crystal vibrates at a remarkably stable frequency. The principle is called piezoelectricity. When you squeeze quartz, it generates a tiny electric voltage. Conversely, when you apply a voltage to quartz, it changes shape slightly. Apply an alternating voltage at just the right frequency, and the crystal resonates, vibrates strongly like pushing a child on a swing at the right moment in each cycle. Most quartz watches use crystals cut to vibrate at exactly 32,768 times per second. Why that specific number? Because it's a power of 2. 32,768 equals 2 to the 15th power. This makes it easy to divide electronically down to exactly 1 pulse per second. You don't need to remember the number. Just know that it's fast, far faster than a pendulum, and remarkably steady. Quartz clocks were far more precise than most mechanical watches. They didn't need daily winding. They weren't affected much by temperature or position. They were compact, reliable, and eventually cheap to manufacture. By the 1960s and 70s, quartz watches had revolutionized the industry. Mechanical watches that cost thousands of dollars couldn't match the accuracy of a $50 quartz watch. But even quartz crystals had limits. They were still physical objects, subject to aging, to temperature effects, to tiny variations in their crystal structure. A quartz crystal vibrates because of its physical structure, the arrangement of silicon and oxygen atoms in a lattice. That structure can shift slightly over years. Impurities in the crystal can affect its frequency. The electrodes attached to the crystal can degrade. A good quartz watch might gain or lose 15 seconds per month. That's good enough for everyday life. But not good enough for science, not good enough for telecommunications, not good enough for navigation, not good enough for the emerging digital world. There was a fundamental limit to how accurate a clock could be if it depended on any macroscopic physical object, any spring, wheel, pendulum, or vibrating crystal. Scientists began to ask a deeper question, a question that would transform timekeeping forever. Could we base time not on the motion of something big, something we can see and touch, but on the unchanging behavior of something very, very small? Could we use atoms themselves as clocks? After all, every atom of a given element is identical. Every cesium atom in the universe, anywhere, at any time, has the same number of protons, the same number of electrons, the same internal structure. If atoms have an internal rhythm, some natural frequency at which they oscillate, and if that rhythm is set by the laws of physics rather than by human craftsmanship, then we could build a clock that doesn't drift, doesn't age, doesn't depend on where you are or what the temperature is. A clock based on nature itself. A clock that would work the same way on Earth as on Mars, in the Arctic as at the equator, today as 10,000 years from now. The answer lay in quantum mechanics. Your breathing might be slowing now. That's good. Let it slow. At the scale of atoms, every element has its own internal music, specific frequencies at which its electrons naturally jump between energy levels. This isn't a metaphor or a simplification. It's literal. It's physics. Atoms absorb and emit light, electromagnetic radiation, at very precise wavelengths, determined entirely by the structure of their electron clouds. Here's how it works. An atom consists of a dense nucleus made of protons and neutrons, surrounded by a cloud of electrons. These electrons don't orbit the nucleus like planets around a sun. That's an outdated model. Instead, they exist in what quantum mechanics calls states or orbitals, regions of space where they're likely to be found. Each orbital has a specific energy. Some orbitals are close to the nucleus and have low energy. Others are farther out and have higher energy. When an electron jumps from a higher energy orbital to a lower one, it must release energy. That energy comes out as a photon, a particle of light. The energy of that photon exactly equals the difference between the two orbital energies. And because photon energy is directly related to frequency, Einstein's famous equation E equals hf, where h is Planck's constant, the frequency of the emitted light is completely determined by the energy levels in the atom. Here's the key insight: those energy levels are not arbitrary. They're not set by human choice or engineering. They're determined by the fundamental laws of quantum mechanics, by the number of protons in the nucleus, by the electromagnetic force, by constants of nature. So every hydrogen atom in the universe emits light at the same specific frequencies. Every sodium atom emits a different set of specific frequencies. Every cesium atom emits yet another set. These frequencies are called spectral lines, and they're as unique to each element as fingerprints are to humans. Sodium atoms emit yellow light, specifically light with a wavelength of about 589 nanometers. That's why sodium streetlights glow that particular shade of amber. Neon atoms emit red-orange light. Mercury atoms emit blue-green. Hydrogen emits a distinctive red line, called hydrogen alpha, that astronomers use to map the universe. Each element has its own signature, its own set of frequencies, immutable and eternal. Now here's where it gets interesting for timekeeping. Physicists in the early 20th century discovered that if you take an atom and expose it to electromagnetic waves, radio waves, microwaves, light, exactly tuned to one of those natural transition frequencies, the atom responds very strongly. It's like ringing a bell at its natural frequency. The bell resonates, vibrates intensely because you've matched its internal structure. Hit the bell at a different frequency and it barely rings. But hit it at exactly the right frequency and it sings. Atoms work the same way. Shine light on an atom at the wrong frequency and nothing happens. The photons pass by without interacting. Shine light at exactly the right frequency, one that matches the energy difference between two of the atom's levels, and suddenly the atom absorbs that light, jumps to a higher energy state, and may later emit a photon when it falls back down. The idea of an atomic clock reduced to its simplest form is this. Instead of using a pendulum swinging once per second, or a quartz crystal vibrating thousands of times per second, what if we used an atom's natural transition frequency as our reference and counted its cycles? If we can lock an oscillator, a device that produces electromagnetic waves, to one of these atomic transitions, we'll have a clock that's as stable and reproducible as the laws of quantum mechanics themselves. So why cesium? Why not hydrogen, which is the simplest element? Why not carbon, which is fundamental to life? Why not gold, which doesn't corrode? Several reasons, all practical. First, cesium exists in nature as a single, stable isotope. Most elements come in multiple versions called isotopes, same number of protons but different numbers of neutrons in the nucleus. Carbon has carbon-12 and carbon-13 and carbon-14. Oxygen has oxygen-16 and oxygen-17 and oxygen-18. Different isotopes have slightly different masses, which means they behave slightly differently. Their spectral frequencies are shifted by tiny amounts. But naturally occurring cesium is almost entirely cesium-133. More than 99.9%. So every cesium atom you work with is effectively identical to every other cesium atom. No need to separate isotopes. No need to worry about which version you're measuring. Second, cesium has a transition in its lowest energy state that produces microwaves with a frequency that's practical to work with. The transition involves something called hyperfine structure. Both the nucleus and the outermost electron in a cesium atom have a property called spin. They behave like tiny magnets. These two magnets can be aligned in the same direction or in opposite directions. When they're aligned, the atom has slightly more energy. When they're opposite, it has slightly less. The energy difference is tiny, unimaginably small by everyday standards. But it corresponds to microwave radiation at a frequency of exactly 9,192,631,770 cycles per second. That's about 9.2 gigahertz if you're familiar with radio terminology. This frequency is high enough to be precise. More cycles per second means finer resolution, but low enough that the technology to generate and measure it was available in the 1950s. You can build microwave generators and detectors with vacuum tubes and later with solid-state electronics. Third, cesium is relatively easy to vaporize. At room temperature, cesium is a soft, silvery metal. It sits in the leftmost column of the periodic table, alongside lithium, sodium, potassium, rubidium. These are called alkali metals, and they all share certain properties. They're highly reactive, soft enough to cut with a knife, and they have a single electron in their outermost shell, which is what makes them useful for atomic physics. Cesium melts at only about 28 degrees Celsius, just above room temperature. Heat it a bit more and it evaporates readily, producing a vapor of individual cesium atoms. This makes it practical to build a cesium beam or fountain. You can create a source of atoms without needing extreme temperatures. Cesium is so reactive that it can ignite spontaneously in air, producing cesium oxide and a lot of heat. It reacts violently with water, more violently even than sodium, producing hydrogen gas and heat that can cause the hydrogen to ignite. In its pure form, cesium is dangerous to handle. But inside a vacuum chamber, isolated from oxygen and moisture, carefully controlled, cesium atoms become one of the most reliable references in all of physics. The specific transition we use, the hyperfine transition between two levels of the ground state, has another important property. It's very clean. The spectral line is narrow, meaning the atom responds strongly only when the frequency is very close to the resonance. This is like having a very selective radio receiver that picks up only one station and rejects everything else. The narrower the line, the more precisely you can determine the exact center frequency, and the more accurate your clock can be. Now, about that specific number, 9,192,631,770. That number isn't a fundamental constant of nature, not like the speed of light or Planck's constant. It was chosen by humans in 1967, when the second was officially redefined in terms of cesium. Hey race, what happened? Before atomic clocks, the second was defined astronomically as a fraction of the average solar day. Specifically, a second was 1 divided by 86,400 times the mean solar day. There are 24 hours in a day, 60 minutes per hour, 60 seconds per minute, so 24 times 60 times 60 equals 86,400. But Earth's rotation isn't perfectly steady. It slows down gradually. It wobbles. Some days are longer than others by a few milliseconds. In the late 1950s, astronomers at the U.S. Naval Observatory performed extremely careful measurements of the moon's motion over many years. The moon's orbit is very stable and predictable, more stable than Earth's rotation. Using these observations, they defined a unit of time called the ephemeris second, based on the moon's motion rather than Earth's rotation. Meanwhile, physicists at the National Physical Laboratory in the UK, particularly Louis Essen and Jack Parry, had built one of the first practical cesium atomic clocks. They measured its frequency as carefully as possible and compared it to the ephemeris second. They found that the cesium hyperfine transition frequency, when counted for exactly one ephemeris second, came out to 9,192,631,770 cycles. So when the international community decided to redefine the second in terms of atomic physics, to make it based on an atomic standard rather than on astronomy, they chose this number specifically to make the new second match the old second as closely as possible. It was a choice of continuity. They wanted the new definition to align with all existing measurements, all existing clocks, all existing tables and calculations. But once that choice was made, it became fixed. Exact. Defined. The second is now defined, officially internationally by agreement of the world's measurement institutions, as the duration of exactly 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Not approximately. Exactly. By definition. From that tiny atomic rhythm, invisible, inaudible, accessible only through sophisticated apparatus, we build everything else. Minutes. Hours. Days. GPS satellites calculating their orbits and your position on Earth. Internet servers synchronizing data transfers. Financial markets timestamping transactions to microseconds. Scientists measuring the speed of light, the gravitational constant, the fine structure constant. All synchronized, ultimately, to the behavior of cesium atoms in laboratories around the world. Your breath is slowing. That's exactly what should happen. Let it continue slowing. Turning this idea, using atoms as clocks, into an actual working machine took decades of effort by some of the best physicists and engineers in the world. The theory was understood by the 1930s and 40s. Physicists knew that atoms had these precise transition frequencies. They knew, in principle, that you could use them for timekeeping. But measuring them accurately enough, and building a clock around them that was better than existing quartz clocks, was extraordinarily difficult. The challenge wasn't just physics, it was engineering. You needed to create a beam of cesium atoms, isolate them from external magnetic fields, expose them to precisely controlled microwaves, detect whether they'd absorbed energy, and do all of this with enough stability and precision to beat the best quartz clocks of the era. In 1955, at the National Physical Laboratory in Teddington, England, two scientists named Louis Essen and Jack Parry achieved this goal. They built one of the first practical cesium-beam atomic clocks. Essen was already well known for his work on measuring the speed of light. In the 1940s, he and a colleague named Albert Gordon Smith had determined the speed of light to unprecedented accuracy using microwave cavity techniques. Now he turned those skills to timekeeping. The device they built was about the size of a large desk. At one end was a small oven containing cesium metal. When heated to about 100 degrees Celsius, the cesium would evaporate, producing a steady stream of atoms. These atoms emerged from a small slit in the oven and traveled down a long vacuum tube, perhaps a meter in length, with all the air pumped out to create a high vacuum. The atoms were moving fast at room temperature, a few hundred meters per second. Too fast, really, but there was no way to slow them down at the time. Laser cooling wouldn't be invented for another 25 years. As the atoms flew down the tube, they passed through a magnetic field created by carefully shaped magnets. This field sorted the atoms according to their quantum state. Remember, cesium atoms can have their nuclear and electron spins aligned or anti-aligned. These different states respond differently to magnetic fields. Atoms in one state would be deflected slightly upward. Atoms in the other state would be deflected slightly downward. A slit or aperture would allow only atoms in the desired state, let's say the lower energy state, to continue down the tube. The others would hit the walls of the chamber and stick there. The selected atoms then entered the critical region, the microwave cavity. This was essentially a metal box, carefully designed to support a standing wave of microwave radiation at a frequency close to the cesium transition frequency. A microwave oscillator, a device similar to what's inside a microwave oven, but much more stable and controllable, fed energy into the cavity at a precisely determined frequency. As atoms flew through this cavity, they were bathed in microwave radiation for perhaps a few milliseconds. If the microwave frequency was exactly right, exactly matched to the natural cesium transition at 9.2 GHz, many atoms would absorb energy and flip from the lower energy state to the higher one. If the frequency was off by even a few hertz out of 9 billion, fewer atoms would make that transition. The cesium atoms were exquisitely sensitive. The transition has what physicists call a narrow line width, meaning the atoms respond strongly only when you hit the exact frequency. After passing through the microwave cavity, the atoms continued down the tube and passed through another magnetic field, similar to the first one but oriented differently. This second magnet sorted the atoms again, this time selecting only those that had ended up in the higher energy state, the ones that had absorbed microwave energy. These selected atoms finally struck a hot wire detector at the end of the tube. When a cesium atom hits a hot metal surface, it tends to give up its outermost electron, becoming positively charged, a cesium ion. That free electron produces a tiny electric current that can be measured. The detector essentially counted arriving atoms by measuring this current. More atoms arriving meant larger current. Fewer atoms meant smaller current. Essen and Parry's clock used this signal as feedback. An electronic control system looked at the detector current. If the current was low, it meant the microwave frequency was off resonance. The system would adjust the frequency slightly. If the current was high, it meant the frequency was close. If the current was at its maximum, the frequency was locked precisely to the cesium transition. The system would make tiny adjustments continuously, always seeking the peak, like a person at the top of a hill taking small steps in every direction to make sure they're truly at the highest point. It was like tuning a radio to get the strongest signal, but with astonishing precision. When everything was working correctly, the microwave frequency was locked to the cesium transition to within a few parts in 10 billion. That frequency, those 9 billion oscillations per second, was then divided down electronically. Electronic circuits counted the microwave cycles. After exactly 9,192,631,770 cycles, a pulse was produced. That pulse represented 1 second. From there, you could count seconds to make minutes, minutes to make hours, and so on. The accuracy was extraordinary for 1955. Essen and Parry's clock was stable to within about 1 part in 10 to the 9th. In practical terms, it would neither gain nor lose more than 1 second in about 300 years. That was better, far better, than any pendulum clock, any quartz clock, any astronomical observation. It was also reproducible. If someone else built an identical clock anywhere in the world, in America, in Germany, in Japan, and used the same cesium transition, their clock would tick at exactly the same rate as Essen's clock in England. Not similar. Not close. Exactly the same within the limits of measurement. This was revolutionary. Soon after Essen and Parry's success, other laboratories built their own cesium atomic clocks. In the United States, the National Bureau of Standards, later renamed the National Institute of Standards and Technology, or NIST, developed a series of cesium-beam clocks. They had names like NBS-1, built in 1952, Pause, NBS-2, completed in 1960, Pause, NBS-4, NBS-5, NBS-6, each one more accurate than the last. Engineers learned to eliminate sources of error. They improved the vacuum systems, pumping out more and more air until the pressure inside was lower than outer space, reducing the chance that cesium atoms would collide with stray molecules. They developed better magnetic shielding, layers of special alloys that blocked external magnetic fields from interfering with the atoms. They refined the microwave sources, making them more stable, more pure in frequency, with fewer unwanted harmonics or noise. They lengthened the interaction region, giving atoms more time in the microwave field to sample the frequency. Each improvement brought more accuracy. By the early 1960s, it was becoming clear that atomic clocks were not just competitive with astronomical timekeeping, they were better. Earth, it turned out, is not a perfect timekeeper. Its rotation slows gradually over time due to tidal forces from the moon. The moon pulls on Earth's oceans, creating bulges of water. As Earth rotates under these bulges, friction between the ocean and the seafloor dissipates energy, slowing Earth's rotation. The effect is tiny, about 2 milliseconds per century. But it's real, measurable, and cumulative. 500 million years ago, a day was only about 22 hours long. In the future, days will be longer. Earth also wobbles slightly on its axis, a motion called nutation. And its rotation rate fluctuates by tiny amounts from year to year, sometimes speeding up, sometimes slowing down, due to mass redistribution from earthquakes, from melting ice, from atmospheric circulation patterns, from fluid motion in Earth's core. For everyday life, these variations don't matter. But for precision science, they made Earth-based timekeeping increasingly problematic. In 1967, the international community made a historic decision. The General Conference on Weights and Measures, the international body responsible for defining units of measurement, voted to redefine the second. It would no longer be defined astronomically as a fraction of the solar day. Instead, the second would be defined atomically in terms of cesium. The official definition, which remains in effect today, states: the second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. In simpler language, a second is the time it takes for a cesium atom to complete that many oscillations. This was a profound shift. For thousands of years, humans had defined time by looking at the sky, at the sun, the stars, the moon. Now, time was defined by looking at atoms. Timekeeping had moved from astronomy into quantum physics. And this wasn't just a philosophical change. It had practical implications. The new definition meant that anyone, anywhere with the right equipment could reproduce the standard. You didn't need access to a particular observatory or a specific physical artifact. You needed cesium atoms, which exist everywhere, and the knowledge of how to interrogate them. The second became democratized, distributed, reproducible. No longer dependent on a single location or a single measurement authority, but on a natural constant that exists throughout the universe. This shift enabled international cooperation at a level previously impossible. Different countries, different laboratories, different continents could all maintain their own atomic clocks and know they were measuring the same unit of time. and improve they did. Through the 1970s and 80s, cesium-beam clocks steadily improved, reaching uncertainties of a few parts in 10 to the 14th by the 1990s. But they were approaching a fundamental limit. The atoms in beam clocks move fast, hundreds of meters per second. They pass through the microwave cavity in just a few milliseconds. That's not much time to determine the exact frequency. The challenge facing Essen and Parry wasn't just theoretical. Building the first practical cesium clock required solving dozens of engineering problems that had never been tackled before. First, they needed pure cesium metal. Not just cesium compounds, but elemental cesium, the soft, silvery metal that reacts violently with air and water. Obtaining it was tricky. Cesium had to be sealed in glass ampoules under vacuum or inert gas. Opening these ampoules without contaminating the metal required working in a glove box filled with argon. They designed an oven to hold the cesium, a small stainless steel chamber with heating coils wrapped around it. The temperature had to be controlled precisely because too hot and the cesium would evaporate too quickly, flooding the system. Too cool and not enough atoms would emerge. Around 100 degrees Celsius was optimal. At that temperature, cesium vapor pressure was high enough to produce a steady atomic beam, but low enough that the metal would last for months or years. The vacuum system required multiple pumps working in series. First, a mechanical rotary pump to bring the pressure down from atmospheric to about 1/10,000th of atmospheric pressure. Then an oil diffusion pump, a device that boiled special low vapor pressure oil, creating vapor jets that swept residual air molecules toward the exhaust. This could reach pressures of 100 millionth of atmospheric pressure. But even that wasn't quite enough. Cesium atoms flying through the tube would occasionally collide with residual gas molecules, nitrogen, oxygen, water vapor, knocking them off course. So they added cold traps, chambers cooled with liquid nitrogen to about -200 degrees Celsius. At that temperature, most remaining gas molecules would freeze onto the cold surfaces, further improving the vacuum. The magnetic fields required careful design. They needed to separate atoms in different quantum states without affecting the measurement of the transition frequency itself. Essen used permanent magnets arranged in specific geometries, sometimes called C-field configurations because of their shape. The magnetic field strength and gradient had to be calibrated carefully. Too strong a field, and it would shift the atomic transition frequency, the very thing they were trying to measure precisely. Too weak, and the separation wouldn't be clean. The microwave cavity was perhaps the most critical component. It was essentially a metal box with precise dimensions, designed to resonate at exactly the cesium transition frequency of about 9.2 gigahertz. The quality factor, a measure of how sharply the cavity resonated, had to be high. This meant the metal surfaces had to be very smooth, very clean, and made of materials with low electrical resistance. Copper was the usual choice, often gold-plated to prevent oxidation. The cavity dimensions were calculated from electromagnetic theory, but in practice required empirical tuning. Small screws could be adjusted to change the cavity's resonant frequency by small amounts. The microwave source itself was another challenge. In the 1950s, generating stable microwaves at 9 GHz wasn't easy. They used devices called klystrons or reflex oscillators, vacuum tube technology that could produce microwaves when driven with high voltages. But these oscillators drifted in frequency. Temperature changes, power supply fluctuations, aging of components, all caused the frequency to wander. That's where the atomic clock concept came in. The atoms would provide the stable reference. The microwave source would be locked to that reference through feedback control. The detection system had to count individual cesium atoms striking the detector. The hot wire detector worked on the principle of thermionic emission. Cesium atoms hitting a hot tungsten surface would give up their electrons, producing a measurable current. But the current was tiny, nanoamperes or less. It had to be amplified by sensitive electronics, electrometer amplifiers, probably using vacuum tubes in that era, with careful shielding against electrical noise. Then came the control system, the electronic circuits that adjusted the microwave frequency to maximize the detector signal. This was before digital computers were common in laboratories. Everything was analog voltage comparators, servo amplifiers, integrators built from resistors and capacitors and vacuum tubes. The system would slowly sweep the microwave frequency back and forth across the resonance, measure the detector response, and use that information to steer the frequency toward the peak. It was elegant in concept but finicky in practice. Every component had to be adjusted just right. The magnetic fields had to be shimmed to uniformity. The vacuum had to be maintained. The temperature had to be stable. Essen and Parry spent months, probably years, perfecting their device. And when it finally worked, when the microwave frequency locked stably to the cesium transition and stayed there hour after hour, day after day, they had something extraordinary. Not just a clock, but a new way of defining time. A way that didn't depend on Earth's rotation, on pendulums, on quartz crystals. A way based on an immutable property of nature itself. Other labs quickly followed. At the National Bureau of Standards in Boulder, Colorado, a team led by Norman Ramsey developed cesium clocks using a technique that would later bear his name, the Ramsey method of separated oscillatory fields. Instead of one long microwave cavity, Ramsay used two shorter ones separated by a field-free region. Atoms would interact with microwaves in the first cavity, coast through the middle region, then interact again in the second cavity. This created a quantum interference pattern that was even more sensitive to frequency than a single cavity. It would later become standard in all high-performance atomic clocks, including fountain clocks. It's like trying to measure the pitch of a musical note by listening to it for only 1/100th of a second. You can get close, but you can't be as precise as if you listened for a full second or longer. In the language of frequency measurement, the longer you can observe an oscillator, the more precisely you can determine its frequency. To make atomic clocks significantly better, physicists needed a way to slow down the atoms, to give them more time in the microwave field. That's where laser cooling came in. And that's where fountain clocks changed everything. Your eyes might be feeling heavy now. Let them close if they want to. First, before we get to fountain clocks, let's take a slow, detailed walk through a classic cesium-beam clock. Understanding how the beam clock works will help you appreciate why fountain clocks were such a revolutionary improvement. Picture a long metal tube, perhaps 1 meter in length, maybe 5 or 6 centimeters in diameter. The entire tube is under high vacuum, pumps running continuously to remove air molecules until the pressure inside is about 100 billionth of atmospheric pressure. Why such extreme vacuum? Because if cesium atoms collide with air molecules, they'll be knocked off course. Their trajectories will become random. The measurement will become noisy, imprecise. At one end of this tube is the cesium oven. It's a small cylindrical chamber, perhaps 10 centimeters long and 5 centimeters in diameter, made of stainless steel or sometimes nickel. Inside is a quantity of pure cesium metal, maybe a few grams, which is enough to last for years. The oven is wrapped with heating wire, like the heating element in a toaster. Electric current flowing through this wire heats the oven to about 100 degrees Celsius. At that temperature, cesium atoms begin to evaporate from the surface of the metal, much like water evaporates from a puddle, except this is happening in vacuum. The atoms don't evaporate in any organized way. They fly off in random directions with random speeds, following what physicists call a Maxwell-Boltzmann distribution. Most atoms are moving at around 200 to 300 meters per second, faster than the speed of sound in air. Some are slower, some are faster, but there's an average speed determined by the temperature. At the front of the oven is a small slit, perhaps 1 millimeter wide. Atoms flying toward this slit escape into the vacuum tube. Atoms flying in other directions hit the walls of the oven and bounce around until they either escape or stick to the surface. The result is a thin beam of cesium atoms emerging from the oven, traveling down the tube. This beam is invisible to the naked eye. is not a laser beam or a light ray. It's simply a stream of individual atoms, each one about 3/10 of a nanometer in diameter, flying in approximately the same direction. The atoms first encounter a magnetic field region called the A magnet or the state selector. This magnet is carefully designed with a specific shape, often a two-wire configuration or a four-pole arrangement, that produces a non-uniform magnetic field. Remember, cesium atoms can be in two different hyperfine states, depending on whether their nuclear spin and electron spin are aligned or anti-aligned. These two states respond differently to magnetic fields. Atoms in one state experience a force pushing them slightly upward as they pass through this magnetic field region. Atoms in the other state experience a force pushing them slightly downward. After traveling through this field for perhaps 10 or 15 centimeters, the beam has split into two separate paths. A slit or aperture positioned carefully in the tube allows only atoms that were pushed in one direction, let's say downward, to continue. These are all atoms in the lower hyperfine state, the state we want to measure. The others hit a metal wall and stick there, eventually accumulating as a thin film of cesium that would need to be cleaned periodically if this were a real apparatus. The selected atoms continue down the tube toward the microwave cavity. This is the heart of the clock, the critical region where the actual measurement happens. The cavity is a metal box, perhaps 30 centimeters long and 10 centimeters on each side, with small holes at both ends to let the atomic beam pass through. Inside this box, a standing wave of microwave radiation is maintained. A microwave oscillator, essentially a specialized radio transmitter tuned to about 9.2 gigahertz, feeds power into the cavity through a small antenna or a waveguide. The cavity is designed so that it resonates at this frequency, like an organ pipe resonates at a particular musical note. The walls of the cavity are made of metal, usually copper plated with gold or silver to minimize losses. The dimensions are chosen so that the microwaves reflect back and forth, adding constructively to create a strong electromagnetic field inside. As cesium atoms fly through this cavity, they spend perhaps 2 or 3 milliseconds inside, depending on their speed. During this time, they are bathed in microwave radiation oscillating at roughly the same frequency as their natural transition. If the microwave frequency matches the atomic transition exactly, something remarkable happens. The atom doesn't absorb energy all at once. Instead, quantum mechanics says the atom enters a superposition, a state where it's simultaneously in both the lower and upper energy levels, with a phase relationship between them. This superposition oscillates in time at exactly the frequency difference between the microwaves and the atomic transition. By the time the atom exits the cavity, if the frequency was exactly right, the atom will have completely transitioned to the upper state. If the frequency was slightly off, the transition will be incomplete. The atom might be only halfway switched or might have switched and switched back. This creates what's called a Rabi oscillation, named after physicist I.I. Rabi, who first described the phenomenon. But there's a complication. Because different atoms in the beam have slightly different speeds, they spend different amounts of time in the cavity. Some atoms zip through in 1 millisecond. Others linger for 5 milliseconds. This causes a broadening of the resonance. The atomic response isn't as sharp as it would be if all atoms experienced the field for exactly the same time. After exiting the microwave cavity, the atoms continue down the tube toward the beam magnet or the analyzer. This magnet is similar to the first one but oriented differently. It sorts atoms according to their state again, but this time selecting only atoms in the upper energy state, the ones that absorbed microwave energy in the cavity. Atoms still in the lower state are deflected away and hit the chamber walls. Atoms in the upper state pass through an aperture and reach the detector. The detector is typically a hot wire, a thin tungsten filament heated to perhaps 1000 degrees Celsius by passing electric current through it. When a cesium atom hits this hot metal surface, there's a high probability it will give up its outermost electron, becoming a positively charged cesium ion. The freed electron is attracted to a collector plate nearby, producing a tiny electric current. This current is amplified and measured by sensitive electronics. The more atoms arriving in the upper state, the larger the current. Fewer atoms means smaller current. This detector current is the clock's primary signal. Now here's where feedback control comes in. The microwave oscillator's frequency is slowly tuned back and forth over a small range around the cesium transition frequency. As the frequency changes, the detector current rises and falls, tracing out a resonance curve. At the peak of this curve, the frequency where the most atoms are transferred to the upper state, the microwave oscillator is locked precisely to the cesium transition. An electronic servo system continuously monitors the detector signal and adjusts the oscillator frequency to keep it at the peak. If the signal drifts left, the frequency is nudged right. If it drifts right, the frequency is nudged left. The system is always seeking the maximum, always correcting for any drift in the oscillator. Once locked, the oscillator frequency is exactly 9,192,631,770 Hz, to within the measurement uncertainty. This frequency is then divided down electronically. A chain of frequency dividers, circuits that take an input frequency and produce an output at a simple fraction, like 1/2 or 1/10, reduces the 9 GHz microwave signal down to manageable frequencies. First to 919 million Hz. Then to 91 million. Then to 9 million. Then to 1 million. Eventually it's divided all the way down to 1 Hz, 1 pulse per second. That pulse is the clock's output, 1 second. From the outside, looking at the apparatus on a lab bench, you would see a metal tube about a meter long, surrounded by magnetic shielding with cables and wires running to electronics racks nearby. Let's look more closely at what's actually happening inside this apparatus at the level of individual atoms. Imagine you are a single cesium atom. You've been sitting on the surface of metallic cesium inside the oven, bonded to other cesium atoms in a crystal lattice. As the oven heats up, thermal energy causes the lattice to vibrate more violently. Eventually, you gain enough energy to break free from the surface. You evaporate. You're now a gas-phase cesium atom, flying in a random direction at several hundred meters per second. You bounce off the walls of the oven several times, each collision randomizing your direction further. Then, by chance, you're flying toward the small exit slit. You pass through it and enter the high vacuum tube beyond. No more collisions now. The pressure is so low there are hardly any other molecules around. You fly in a straight line like a tiny spacecraft coasting through empty space. You enter the first magnetic field region. As a cesium atom, you have an outermost electron and a nucleus, both with quantum mechanical spin. These spins can be aligned or anti-aligned, giving you two possible states. Let's say you're in the lower energy state, spins anti-aligned. As you pass through the non-uniform magnetic field, you experience a force pushing you slightly downward. Your trajectory bends by a few millimeters. Another atom in the upper energy state would be pushed upward instead. This spatial separation happens over the course of a few centimeters of flight, taking perhaps a millisecond at your speed. An aperture, a thin metal plate with a slit, blocks the upward path but allows you through. You continue into the microwave cavity. The cavity is filled with electromagnetic radiation oscillating at about 9 billion cycles per second, much faster than anything you could perceive directly if you were conscious. As you fly through this oscillating field, something strange happens. The energy of the microwaves is very close to the energy difference between your two hyperfine states. In classical physics, nothing would happen. Either the energy matches exactly and you absorb a photon, or it doesn't and you don't. But in quantum mechanics, near matches matter. You enter a superposition, a state where you're simultaneously in both the lower and upper energy levels, with a phase relationship between them. This superposition oscillates at the frequency difference between the microwaves and your natural transition. If the microwaves are exactly on resonance, you'll smoothly transition from lower to upper state during your time in the cavity. If they're slightly off resonance, you might transition partway or transition and then transition back, ending up in a mixture. The probability of ending up in the upper state depends on how long you spend in the cavity and how close the microwave frequency is to your natural resonance. You exit the cavity after a few milliseconds. Your quantum state is now different. You have some probability of being in the upper state, some probability of still being in the lower state. You continue down the tube toward the second magnetic field region, the analyzer. This magnet is configured differently from the first one. It deflects atoms in the upper state downward through a slit, while atoms in the lower state are deflected upward and blocked. You pass through, or you don't. It depends on your quantum state. If you make it through, you strike the hot wire detector. The detector is a thin filament of tungsten heated to about 1000 degrees Celsius, hot enough to glow a dull red if you could see it. When you hit this hot surface, there's a high probability that you'll give up your outermost electron. The work function of hot tungsten is lower than the ionization energy of cesium. You become a positively charged ion, a cesium atom missing one electron. That free electron is attracted to a collector plate held at a positive voltage. It contributes to a tiny electric current. Meanwhile, you as an ion are probably absorbed into the detector surface, adding one cesium atom to the thin film that gradually accumulates there. Your journey is over. But millions of your fellow cesium atoms are making the same journey every second, providing a continuous signal that the clock's electronics can measure and use to lock the microwave frequency. This is the microscopic reality underlying the abstract concept of timekeeping. Countless individual atoms, each one following quantum mechanical rules, each one contributing a tiny bit of information about what frequency corresponds to the cesium transition. You wouldn't hear anything except maybe the hum of vacuum pumps and cooling fans. You wouldn't see the cesium beam, it's invisible, a silent stream of atoms flying through vacuum. But inside that tube, billions of atoms per second are being interrogated, sorted, detected, providing the signal that defines the second. The beam clock was a masterpiece of mid-20th century physics and engineering. But it had a fundamental limitation. The atoms moved too fast. At room temperature, thermal motion gives them hundreds of meters per second of velocity. This limits the interaction time to just a few milliseconds. And that limits the precision with which the transition frequency can be measured. By the 1980s and 90s, beam clocks had reached uncertainties of a few parts in 10 to the 14th, about 1 second in 300,000 years. That's extraordinarily good. But physicists knew it could be better. They needed a way to slow down the atoms, or better yet, to make them pass through the interrogation region twice instead of once. The solution came from a completely different field of physics: laser cooling. Let your jaw relax. Let your tongue rest softly in your mouth. In the 1980s, a revolution was quietly happening in physics laboratories around the world. Physicists were learning to use lasers not to cut metal or read barcodes, but to cool atoms. This sounds backwards. Lasers produce light, and light carries energy. How can shining light on something make it colder? The answer involves a clever trick with photon momentum and the Doppler effect. Every photon carries not just energy but also momentum. When an atom absorbs a photon, the atom receives a tiny kick in the direction the photon was traveling. It's like being hit by a baseball, even a very light baseball. Now, atoms moving through space see laser light Doppler shifted. If an atom is moving toward a laser beam, it sees the light frequency shifted slightly higher. If moving away, it sees the frequency shifted lower. Here's the trick. You tune your laser slightly below the frequency that the atom naturally absorbs. An atom at rest won't absorb this light. The frequency is wrong. But an atom moving toward the laser sees the frequency Doppler shifted upward, bringing it into resonance. So it absorbs a photon and gets a kick opposing its motion. An atom moving away from the laser sees the frequency shifted even further from resonance, so it doesn't absorb. The result? Atoms moving toward the laser get slowed down. Atoms moving away are left alone. Now arrange 6 laser beams in 3 pairs, opposing each other along 3 perpendicular axes, up and down, left and right, forward and back. Every direction an atom tries to move, it encounters a laser beam that opposes its motion. Physicists call this optical molasses because the atoms move through the intersecting laser beams like objects moving through thick syrup. With this technique, you can cool atoms from room temperature, around 300 Kelvin, down to a few millionths of a degree above absolute zero. Their velocity drops from hundreds of meters per second to just a few centimeters per second. This discovery earned Stephen Chu, Claude Cohen-Tanuji, and William D. Phillips the 1997 Nobel Prize in Physics. Pause. And it transformed atomic timekeeping. In the early 1990s, labs like the Paris Observatory's SWRD lab in France, PTB in Germany, and NIST in the United States began developing a new kind of atomic clock based on laser-cooled atoms. They called it a fountain clock. Here's how it works. Inside a tall vacuum chamber, perhaps 2 meters high and maybe 20 centimeters in diameter, a small puff of cesium atoms is released at the bottom. 6 infrared laser beams, each about a centimeter wide, intersect at the center of this chamber. The lasers are tuned to a wavelength of about 852 nanometers, which corresponds to a transition in cesium atoms from the ground state to an excited state. But they're detuned slightly, shifted a few megahertz below the exact resonance, so they create optical molasses. The cesium atoms, initially at room temperature, fly into this intersection of laser beams and begin to slow down. Each atom scatters millions of photons per second. Each scattering event removes a tiny bit of momentum. After perhaps half a second of cooling, you have a cloud of perhaps 10 million cesium atoms, packed into a volume about 1 cubic centimeter, cooled to around 1 microkelvin, 1/1,000,000th of a degree above absolute zero. At that temperature, the atoms are barely moving. Their average velocity is just a few centimeters per second. Now comes the fountain part. The two vertical laser beams, the up and down pair, are slightly detuned relative to each other. By changing the frequency of the upward beam relative to the downward beam, you create what's called a moving optical molasses. Atoms see the upward beam as slightly closer to resonance, so they preferentially absorb photons from below, getting kicked upward. It's like standing on a moving walkway at an airport, except the walkway is made of light and it's moving vertically. The atoms are accelerated gently upward to a velocity of about 4 meters per second, about the speed of a brisk walk. Then all the lasers are turned off. The atoms coast upward under their own momentum, slowing as gravity pulls them back. They rise about 1 meter, like tossing a ball gently into the air, pause at the top and fall back down. The entire flight takes about 1 second. But here's the critical part. On the way up and again on the way down, the atoms pass through a microwave cavity. This cavity is similar to the one in a beam clock, but the atoms pass through it much more slowly and twice. The first time through, on the way up, the atoms spend perhaps 10 milliseconds inside the cavity, experiencing the microwave field. This first pulse puts the atoms into a quantum superposition of the two hyperfine states, just like in a beam clock. Then the atoms coast upward through a field-free region, a drift space where there are no microwaves, no lasers, just gravity and quantum mechanics. During this time, the quantum superposition continues to evolve. The phase relationship between the two states changes in a way that depends on the exact energy difference between them. Then the atoms fall back through the same microwave cavity a second time. This second pulse completes what's called a Ramsey interrogation sequence, named after Norman Ramsey, who developed the technique. The interaction of the second pulse with the atom's quantum state creates an interference pattern that's extremely sensitive to whether the microwave frequency exactly matches the atomic transition. If the frequency is exactly right, nearly all atoms end up in the upper hyperfine state. If it's slightly off, fewer do. The development of fountain clocks wasn't just about better accuracy. It represented a fundamental shift in how physicists thought about atomic clocks. With beam clocks, you were limited by the atom's thermal velocity. Room temperature cesium moves fast, too fast for long interrogation times. Laser cooling changed everything. The technique was developed in the 1980s, building on theoretical work from the 70s. The key insight was that photons carry momentum. When an atom absorbs a photon, it receives a tiny kick in the direction the photon was traveling, about the mass of an electron times the speed of light. That's not much. A single photon doesn't slow an atom noticeably. But an atom moving through laser light tuned slightly below its resonance frequency will preferentially absorb photons when moving toward the laser, because of the Doppler shift bringing the light into resonance. Each absorbed photon slows the atom slightly. The atom then spontaneously re-emits a photon, fluorescence, but in a random direction. On average, these re-emissions don't contribute net momentum in any particular direction. The result: absorption acts like friction, systematically opposing the atom's motion. An atom moving through 6 laser beams, 2 along each axis, experiences friction no matter which direction it tries to move. The name optical molasses captures this beautifully. The atoms move like objects through thick syrup, gradually slowing until they're nearly at rest. But there's a limit. Quantum mechanics imposes a minimum temperature you can reach with this technique, called the Doppler cooling limit. For cesium, that limit is about 125 microkelvin. Below that temperature, the random nature of photon absorption and emission creates heating that balances the cooling. But even that's cold enough that cesium atoms move at just a few centimeters per second instead of hundreds of meters per second. In a fountain clock, the process begins with loading. A small amount of cesium vapor is present at the bottom of the vacuum chamber, perhaps released in pulses from a heated dispenser or maintained as a low-pressure background gas. 6 laser beams converge at the center of the chamber, each about a centimeter wide, each carrying about 40 milliwatts of power at a wavelength of 852 nanometers, deep red, almost infrared. These lasers are detuned from the cesium D2 transition by about 10 to 20 megahertz, tuned below the resonance so they create optical molasses. Cesium atoms drifting through this intersection scatter photons, millions per second per atom. Each scattering event removes a tiny bit of kinetic energy. After perhaps half a second, you have a cloud of about 10 million atoms, packed into a volume of about 1 cubic centimeter, cooled to around 1 microkelvin. That's 1/millionth of a degree above absolute zero. At that temperature, the atoms are moving so slowly that thermal motion is almost negligible compared to other effects. Now comes the launch. The 2 vertical laser beams, the up and down pair, have their frequencies shifted relative to each other. The upward beam is shifted closer to the atomic resonance. The downward beam is shifted further away. This creates a moving optical molasses, a reference frame that's accelerating upward. Atoms in this reference frame experience a net upward force from the imbalance in photon scattering. Over the course of a few milliseconds, the atoms are accelerated to about 4 meters per second upward. Then all the lasers are switched off. The atoms coast upward under their own momentum, slowing as gravity pulls them back. After about half a second, they reach the apex of their flight, about 1 meter above the launch point, and pause momentarily before falling. The total flight time from launch to return is about 1 second. During this flight, the atoms pass twice through a microwave cavity. This cavity is a precisely machined copper structure, cylindrical, perhaps 15 centimeters long and 10 centimeters in diameter. Inside, a standing wave of microwave radiation is maintained at the cesium transition frequency. The cavity is designed to support a TE011 mode, a particular electromagnetic field pattern where the electric field is strong along the axis and weak near the walls. When atoms pass through on the way up, they spend perhaps 10 to 20 milliseconds inside, experiencing this oscillating field. This is the first Ramsey pulse. The atoms emerge in a quantum superposition of the two hyperfine states. The phase relationship between these states is determined by the microwave frequency. During the long drift time between the two cavity passes, about 1 second, the superposition continues to evolve. The phase accumulates in a way that depends on the exact energy difference between the two states. Then the atoms fall back through the cavity, experiencing the second Ramsey pulse. This second interaction creates a quantum interference pattern. If the microwave frequency was exactly on resonance, the two pulses coherently drive the atoms into the upper state. If the frequency was off by even a small amount, the interference is destructive, and fewer atoms end up in the upper state. The result is a resonance pattern, called Ramsey fringes, with a central peak that's extraordinarily narrow. The width of this peak is inversely proportional to the time between the two pulses. With a 1 second separation, the line width is about 1 Hertz. That means you can determine the resonance frequency, 9.2 gigahertz, to within 1 Hertz. That's a precision of about 1 part in 10 billion from a single measurement cycle. After the second cavity pass, the atoms fall to the detection region at the bottom of the chamber. A horizontal laser beam shines across their path, tuned to excite atoms in the F equals 4 hyperfine state but not F equals 3. Atoms in F equals 4 absorb this light and fluoresce, emitting photons in random directions. A lens and photodetector positioned nearby collect this fluorescence. The intensity tells you how many atoms are in F equals 4, which tells you how close the microwave frequency was to resonance. Then the cycle repeats. A new cloud is loaded, cooled, launched. Interrogated. Detected. Over and over, continuously building up statistics. Each cycle takes 1 to 2 seconds. Over the course of hours or days, the clock accumulates thousands of measurements, determining the cesium transition frequency with extraordinary precision. The beauty of this design is that almost all sources of systematic error can be controlled or measured. Collisions between atoms. Vary the atom number and extrapolate to zero density. Doppler shifts from residual motion. The atoms are so slow this is negligible and symmetric between the up and down passes. Black body radiation shifts. Measure or control the temperature, apply corrections. Magnetic fields. Shield carefully, measure the field, correct for Zeeman shifts. One by one, every known systematic effect has been characterized and minimized. After falling back through the cavity, the atoms continue down to a detection region at the bottom of the chamber. Here, a carefully tuned laser beam shines horizontally across the path of the falling atoms. This detection laser is tuned to excite atoms in the upper hyperfine state, but not atoms in the lower state. Atoms in the upper state absorb the laser light and fluoresce. They emit photons in random directions. A photodetector positioned nearby collects this fluorescence light and measures its intensity. The more fluorescence, the more atoms ended up in the upper state, which means the microwave frequency was closer to the atomic resonance. The entire cycle, cooling, launching, interrogating, detecting, takes about 1 to 2 seconds. Then it repeats. A new batch of atoms is loaded into the optical molasses, cooled, launched, interrogated, detected. Over and over, continuously, gathering data to determine the exact resonance frequency. The key advantage over beam clocks is the much longer interrogation time. In a beam clock, atoms spend just a few milliseconds in the microwave field. In a fountain clock, the total interrogation time, counting both passes through the cavity and the drift time between them, is nearly 1 second. That's several hundred times longer. And the longer you can observe an atomic transition, the more precisely you can measure its frequency. It's like measuring the frequency of a musical note. If you only hear the note for 1/100th of a second, you can roughly tell what pitch it is. But if you listen for several seconds, you can determine the frequency to many decimal places. The first operational cesium fountain clock was built by Eswardi in France and began operation in 1995. NIST's first fountain, NIST F1, was completed in late 1999 and began contributing to international time in early 2000. When NIST F1 was evaluated, it achieved an uncertainty of about 3 parts in 10 to the 15th. In practical terms, it would neither gain nor lose 1 second in approximately 20 million years. That was more than 10 times better than the best cesium-beam clocks. Within a few years, other countries built their own fountains. PTB in Germany built their primary standard. NPL in the UK built theirs. Japan, Italy, Russia, China all eventually developed fountain clocks. And the accuracy kept improving. Engineers learned to control and measure systematic effects more carefully. One major source of uncertainty was collisions between cesium atoms in the cloud. When atoms are packed closely together, they bump into each other, and these collisions slightly shift the transition frequency. By using smaller, less dense clouds, or by measuring how the frequency changed with cloud density and extrapolating to zero density, this effect could be characterized and corrected. Another issue was the Doppler effect from the atom's motion. Even though the atoms are moving slowly, they're not completely at rest. Their motion through the microwave field can cause small frequency shifts. Careful design of the microwave cavity and the launch velocity minimized this. Blackbody radiation from the warm chamber walls also causes a tiny shift. The thermal photons interact with the atoms, slightly changing their energy levels. By controlling the temperature precisely or measuring it and applying corrections, this could be accounted for. The Earth's magnetic field, even after shielding, causes small shifts. These were measured and corrected. One by one, every known source of systematic error was characterized, measured, and either eliminated or corrected mathematically. NIST F2, completed in 2014, incorporated many improvements. The biggest was operating at cryogenic temperature. The entire vacuum chamber was cooled to about 80 Kelvin using liquid nitrogen. This reduced the blackbody radiation shift significantly, fewer thermal photons at lower temperatures. NIST F2 achieved an uncertainty of about 1 part in 10 to the 16th. That's accurate to about 1 second in 300 million years. To put that in perspective, if you had started NIST F2 running when dinosaurs walked the Earth 200 million years ago, it would be off by less than 1 second today. More recently, NIST has built F3 and F4. F4 is expected to reach uncertainties approaching 1 part in 10 to the 17th when fully evaluated. Other labs have achieved similar performance. These fountain clocks represent the culmination of cesium-based timekeeping, the best that can be done with microwave transitions in cesium atoms. They are among the most precise measurement instruments ever built for any purpose. And yet, even as they reached this extraordinary level of performance, physicists were already looking beyond cesium, toward optical clocks using visible light instead of microwaves. But we'll get to those in a moment. For now, feel your body settling more deeply into rest. Pause. Notice how little effort it takes to simply be here, listening. No single atomic clock, no matter how accurate, is trusted alone to define world time. This might seem strange. If NIST F4 is accurate to 1 second in hundreds of millions of years, why not just use it? Several reasons. First, even the best clocks can fail or develop problems. A vacuum leak, an electronics malfunction, a laser misalignment, any number of things can go wrong. Second, having multiple independent clocks provides redundancy and validation. If 3 clocks agree and 1 disagrees, you know which one has the problem. Third, no single country or lab should have sole authority over world time. Time is too important, too fundamental. It needs to be international, distributed, cooperative. So instead of relying on one clock, the world uses an ensemble of hundreds. Here's how it works. Around the world, about 80 national metrology institutes and timing laboratories maintain collections of atomic clocks. These institutions include places like NIST in the United States, NPL in the United Kingdom, PTB in Germany, SWRD in France, NICT in Japan, NIM in China, INRIM in Italy, and many others. Each lab operates multiple clocks, typically several commercial cesium-beam clocks, maybe a few hydrogen masers, and often a cesium fountain as their primary standard. In total, there are about 400 high-quality atomic clocks contributing to the worldwide time system. These labs don't just run their clocks, they continuously compare them to each other. Some comparisons are done locally within the same lab. If you have 5 cesium-beam clocks in the same building, you can directly compare their outputs using cables and electronic frequency counters. But how do you compare clocks on different continents? Several methods are used. The oldest method uses GPS satellites. Each lab has a GPS receiver that records the time signals from GPS satellites. By comparing these recordings, labs can determine the time difference between their clocks with uncertainties of a few nanoseconds. A newer, more precise method uses two-way satellite time transfer. 2 labs exchange time signals via a communications satellite. Each lab transmits a pulse at a known time according to its clock. Each lab receives the other's pulse. By comparing transmission and reception times, and knowing the signal travels at the speed of light, they can calculate the time difference with sub-nanosecond precision. The most precise method uses fiber optic cables. Laser pulses travel through optical fibers connecting different labs. This can achieve uncertainties below a picosecond, a trillionth of a second. Europe is building an extensive fiber network connecting major timing labs across the continent. All these comparison data, thousands of measurements per month, flow to a central coordinating organization, the International Bureau of Weights and Measures, or BIPM, located in Sèvres, just outside Paris. The BIPM's time department operates with remarkable quiet efficiency. Picture a small office in a classical French building, perhaps 3 or 4 staff scientists, working with computers that connect to a global network of timing laboratories. Every day, data arrives electronically, formatted files containing clock readings, comparison measurements, uncertainty estimates. The staff don't just average the clocks. They apply sophisticated statistical algorithms that account for each clock's individual characteristics. Some clocks drift predictably over time. Their frequency changes slowly in a known direction. The algorithms can model and compensate for this. Some clocks are noisier than others. They show more short-term fluctuations even though their long-term average might be good. The algorithms weight these appropriately. Some clocks have systematic offsets from the definition of the second, maybe a few parts in 10 to the 16th. These offsets are measured during evaluation campaigns and corrected in the computation. The result is TAI, International Atomic Time. TAI is published retroactively. You can't know the exact value of TAI until all the comparison data has been received and processed, which takes about a month. So laboratories work with real-time predictions of TAI, then later receive corrections when the final values are published. From TAI, UTC is derived by adding leap seconds when needed. The decision to add a leap second is made by the International Earth Rotation and Reference System Service, IRS. They monitor Earth's rotation using multiple techniques: very long baseline interferometry observing distant quasars, satellite laser ranging (GPS), and analysis of lunar laser ranging data from reflectors left on the Moon by Apollo astronauts. When Earth's rotation has slowed enough that the difference between solar time and atomic time approaches 0.8 of a second, IRS announces a leap second will be added. This announcement comes via Bulletin C, published every 6 months, giving advance notice to allow systems to prepare. Since 1972, 27 leap seconds have been added. They don't occur at regular intervals. Sometimes several years pass between them, sometimes they're more frequent. It depends on Earth's rotation rate, which varies due to many factors: redistribution of mass from melting ice, changes in ocean currents, atmospheric circulation patterns, earthquakes that shift mass, convection in Earth's molten core. There's ongoing debate about the future of leap seconds. Some propose abolishing them entirely, letting atomic time and solar time gradually diverge. Proponents argue this would simplify computing systems and avoid the bugs that sometimes occur when software doesn't handle leap seconds properly. Others argue we should keep leap seconds to maintain alignment between civil time and Earth's rotation. If we let them diverge, eventually noon would occur at midnight. That might take thousands of years, but it's a philosophical concern. The discussion continues in international committees, where decisions about fundamental timekeeping are made through consensus among member nations. Meanwhile, UTC continues with its occasional leap seconds, and TAI continues advancing steadily without them. At this moment, TAI is 37 seconds ahead of UTC, the accumulated leap seconds since 1972. The BIPM has been responsible for coordinating international measurements since 1875. They maintain the definitions of the kilogram, the meter, the second, all the fundamental units. Every month, timing labs around the world send their data to the BIPM's time department. This data includes the readings from each of their atomic clocks, comparisons between their clocks, comparisons with GPS satellites, two-way satellite time transfer data with other labs, reports from cesium fountain evaluations, detailed uncertainty budgets showing how accurately each fountain realizes the definition of the second. The BIPM staff, a small team of expert metrologists, analyzes all this data using sophisticated statistical algorithms. They compute a weighted average, giving more weight to more accurate and stable clocks. Cesium fountains get the highest weight because they have the lowest systematic uncertainties. Commercial beam clocks get less weight because they're less accurate. Hydrogen masers get significant weight for short-term stability but are calibrated against cesium for long-term accuracy. The result of this calculation is a time scale called TAI, International Atomic Time, from the French Temps Atomique International. TAI is not the output of any physical clock you can visit. It's a statistical construction, a paper clock, an idealized average representing the consensus of the world's best atomic clocks. TAI advances at a perfectly steady rate, second after second, without interruption. It has been running since 1958, when the first International Atomic Time Scale was established. But TAI is not what your phone uses. It's not what broadcasters use. It's not what appears on official time signals. For everyday use, we use something slightly different, UTC or Coordinated Universal Time. UTC is based on TAI but includes occasional adjustments called leap seconds. Here's why leap seconds exist. While atomic time marches forward at a perfectly steady rate, Earth's rotation does not. Earth is slowing down, very gradually but measurably. Tidal friction from the moon dissipates rotational energy. Each century, the day gets longer by about 1 or 2 milliseconds. If we just used atomic time and ignored Earth's rotation, noon would slowly drift away from the moment when the sun is highest in the sky. After a few centuries, noon might occur in darkness. After a few thousand years, the seasons would be completely out of sync with the calendar. To prevent this, we occasionally insert a leap second into UTC. When Earth's rotation has slowed enough that atomic time and solar time differ by about 0.8 of a second, the International Earth Rotation and Reference System Service, IRS, headquartered in Paris, announces that a leap second will be added. This announcement comes several months in advance, giving computer systems time to prepare. The leap second is usually added either at the end of June or the end of December. On that day, clocks around the world read 23 hours, 59 minutes, 59 seconds. 23 hours, 59 minutes, 60 seconds. 0 hours, 0 minutes, 0 seconds. For one moment, time pauses. Or rather, time continues, but we insert an extra second into our counting. Since leap seconds were introduced in 1972, 27 have been added. They happen irregularly, sometimes several years apart, sometimes more frequently. It depends on Earth's rotation, which is affected by many factors: the distribution of mass in the atmosphere, ocean currents, glacial rebound, earthquakes, movement of fluid in Earth's core. For computer systems, leap seconds are a nuisance. Software developers have to write special code to handle that extra second. Some systems simply stop their clocks for 1 second. Others smear the leap second across a longer period, adding tiny fractions over hours or days. Some major failures have been traced to leap second bugs. There's ongoing debate about whether to abolish leap seconds entirely and just let atomic time and solar time gradually diverge. Astronomers generally want to keep leap seconds. They need clocks aligned with Earth's rotation for pointing telescopes. Telecommunications engineers and GPS operators generally want to abolish them. The synchronization problems are too complex. The decision hasn't been made yet. It requires international agreement, and that takes time. Meanwhile, UTC continues with its occasional leap seconds, and TI advances steadily without them. Your phone, your computer, your car's navigation system, all of them ultimately synchronized to UTC. When your phone says it's 11:37 p.m., it got that time by connecting to a network time server, which got it from a more authoritative server, which eventually traced back to a national timing laboratory like NIST, which compared its clocks to UTC as published by the BIPM. It's an invisible infrastructure, a quiet conversation between machines, ensuring that everyone's clock agrees. You don't have to participate in this conversation. You don't have to maintain it. You can simply trust that it works and let your attention drift away from time entirely. It might feel like atomic clocks are exotic instruments that live far away from ordinary life, tucked behind security doors in national laboratories, relevant only to scientists. But the precision they provide has quietly become essential to the functioning of modern civilization. Let's start with navigation. GPS, the global positioning system, depends entirely on atomic clocks. The system works like this. About 30 satellites orbit Earth at an altitude of roughly 20,000 kilometers. Each satellite carries multiple atomic clocks, typically a combination of rubidium and cesium standards. Each satellite continuously broadcasts a radio signal containing two key pieces of information: its exact position in orbit and the exact time according to its onboard clocks. Your GPS receiver, in your phone, your car, your hiking watch, picks up these signals from multiple satellites. The receiver compares the timestamp in each signal to its own internal clock. The difference tells you how long ago that signal was transmitted. Since radio waves travel at the speed of light, about 300,000 kilometers per second, or more precisely, 299,792,458 meters per second, you can calculate your distance from each satellite. If you know you're a certain distance from satellite A, you must be somewhere on a sphere centered on that satellite. Add a second satellite, and you're somewhere on the intersection of two spheres, a circle. Add a third satellite, and you're at one of 2 points where three spheres intersect. Add a fourth satellite, and you can solve for your exact position in 3 dimensions plus determine your receiver's clock error. The math is straightforward in principle, but it requires extraordinary timing precision. A timing error of just 1 microsecond, 1/1,000,000th of a second, translates to a position error of 300 meters. That's about the length of 3 football fields. If GPS clocks drifted by even a few milliseconds per day, the system would be useless. Your phone would tell you you're kilometers away from where you actually are. The atomic clocks in GPS satellites drift by only about 10 nanoseconds per day, 10 billionths of a second. And even that tiny drift is monitored and corrected by ground stations that track the satellites and upload regular time updates. GPS isn't the only navigation system. Russia has GLONASS. Europe has Galileo. China has Beidou. India has NavIC. All of them use the same basic principle, and all of them depend on atomic clocks. Telecommunications networks also depend on precise time. Modern cell networks use a technology called time division multiple access, or TDMA. Multiple phones share the same radio channel by taking turns transmitting in very short time slots, often just milliseconds long. For this to work without collisions, all the cell towers in an area must be precisely synchronized. If one tower's clock is off by even a few microseconds, phones might try to transmit at the wrong moment, causing interference and dropped calls. Most cell towers have GPS receivers that provide timing signals for synchronization. Data networks use similar principles. When you stream a video, the data arrives as thousands of small packets, each one taking a different route through the internet. Each packet has a timestamp. Your device reassembles them in the correct order based on these timestamps. If the clocks on different routers disagreed significantly, packets would arrive out of order, causing delays and buffering. Financial markets depend critically on accurate time. Stock exchanges timestamp every trade, every buy order, every sell order, every execution, to the microsecond or even nanosecond. This isn't just for record keeping. It determines priority. If two traders try to buy the same stock at the same price, whoever's order arrived first gets priority. The timestamps decide. High-frequency trading firms spend millions of dollars to reduce latency, the delay between their computers and the exchange servers, by microseconds. They place their servers physically close to exchanges. They use the fastest possible network connections. They optimize their software to shave off nanoseconds. Because in this world, a microsecond advantage means millions of dollars. Power grids use synchronized measurements for monitoring and control. Electricity flows through a grid at a frequency of 50 or 60 Hz, depending on the country. The voltage oscillates positive and negative in a sinusoidal wave. At any given instant, different parts of the grid are at different phases of this cycle. To understand what's happening across the entire grid, to detect problems, to balance supply and demand, to prevent blackouts, operators need to measure voltage and current at many points simultaneously. Devices called phasor measurement units, or PMUs, take snapshots of electrical parameters 30 to 60 times per second, all timestamped to within 1 microsecond. By comparing measurements from different locations, engineers can see exactly how disturbances propagate through the grid. If a transmission line fails, they can instantly reroute power. If generation and load are imbalanced, they can adjust. Without accurate time synchronization, the grid would be flying blind. Digital certificates and internet security use time for validation. Every time you visit a secure website, anything with HTTPS in the URL, your browser checks the site security certificate. These certificates have validity periods. Not valid before this date, not valid after that date. If your computer's clock is wrong, it might reject valid certificates or accept expired ones. Blockchain systems like Bitcoin use timestamps to order transactions and prevent double spending. Scientists use precise time for fundamental research. Radio telescopes around the world observe the same cosmic signal simultaneously, then combine their data to create images with resolution far better than any single telescope could achieve. This technique, called Very Long Baseline Interferometry or VLBI, requires that all telescopes' clocks be synchronized to nanoseconds. Particle physics experiments detect events that happen in billionths of a second. Multiple detectors around a collision point must have synchronized clocks to reconstruct what happened. Gravitational wave detectors like LIGO measure distortions in spacetime smaller than the width of a proton. The detectors are thousands of kilometers apart. Comparing their signals requires nanosecond-level time synchronization. Even mundane things like traffic lights, security camera systems, and network file sharing rely on clocks that are ultimately calibrated against atomic standards. You don't see any of this. It happens invisibly, continuously, in the background of modern life. Atomic clocks sit at the bottom of all this infrastructure, like bedrock under a city. You almost never think about them. You almost never need to. In that sense, they're the opposite of the things that demand your attention: the notifications, the alerts, the reminders, the urgent messages. They're quiet servants of coordination, working without thanks, without recognition, enabling everything else to function. Knowing that time is being maintained by experts around the world, that the infrastructure works, that it's reliable, you can give yourself permission to stop keeping track for a while. You don't have to hold the world's schedule together. Others are doing that. You can let go. Let's imagine one person who works in a time lab. Call them Morgan. Morgan is a timing technician on the evening shift at a national metrology laboratory. They arrive at work around 4 p.m., badge in through security, walk familiar hallways to the time department. They're wearing comfortable clothes, jeans, a polo shirt with the lab logo, sneakers with good support because they'll be on their feet for hours. In winter, they bring a sweater because the labs are kept cool to help the equipment stay stable. The day shift technician, finishing up, gives a quick verbal handover. Everything's nominal. Fountain 2 is running a measurement sequence, should finish around 8. Maser 3 had a temperature excursion this morning, but it's back in spec now. GPS antenna 2 is showing intermittent signal. Might need to check the cable tomorrow. Morgan nods, takes notes on a tablet, asks a few questions. The day shift tech leaves. Now it's Morgan's responsibility. They start with the hourly rounds. First stop, the cesium fountain lab. Morgan checks the logbook, a spiral-bound notebook where every technician records observations, even though everything's also logged electronically. There's something reassuring about pen and paper. They look at the computer monitors showing the fountain's status. Vacuum pressure in the main chamber, 2.1 times 10 to the minus 8th torr. Normal. Cooling laser power, 40 milliwatts. Normal. Detection laser power, 2.5 milliwatts. Normal. Microwave power into cavity, minus 12 dBm. Normal. Atom number on this cycle, 8 million. A bit low, but within acceptable range. Morgan writes in the logbook, 1800 hours fountain 2, all parameters nominal. Atom number 8 times 10 to the power of 6. Next stop, the hydrogen maser room. 3 tall equipment racks, each containing a hydrogen maser atomic clock. These aren't cesium fountains, they're a different kind of atomic clock, based on hydrogen atoms instead of cesium. Hydrogen masers aren't as accurate as cesium fountains, but they're extremely stable over short time periods, hours to days. They're used as flywheel oscillators, providing smooth, continuous time signals while the cesium fountain takes measurements. Morgan checks the maser's output frequencies, comparing them to each other and to signals from GPS satellites. Maser 1, frequency offset plus 2.1 times 10 to the minus 15th. Maser 2, frequency offset minus 1.8 times 10 to the minus 15th. Maser 3, frequency offset plus 4.3 times 10 to the minus 15th. All within expected limits. Morgan logs the readings. On to the environmental monitoring station. Temperature in the fountain lab, 20 degrees Celsius, stable to 0.05 degrees. Humidity, 40%. Magnetic field in the fountain chamber, measured by sensors, less than 1 microtesla after shielding. Everything is being recorded automatically, but Morgan checks anyway. Sometimes sensors fail. Sometimes the automatic alerts don't trigger. Human oversight still matters. Morgan walks to the GPS timing receiver rack. A screen shows signals from multiple GPS satellites. Each satellite signal includes a precise timestamp. The receiver compares these to the lab's local clocks. One antenna shows signal marginal status. The same one mentioned during shift change. Morgan makes a note to inspect it tomorrow during daylight, maybe check for loose connections, maybe look at the cable run for any damage. Between rounds, Morgan sits at a desk in the control room, a quiet space with several computer monitors, a coffee maker, a small refrigerator, a bookshelf with reference manuals and old conference proceedings. They pour coffee from a thermos, sit in the ergonomic chair, and watch the screens. One monitor shows a graph of frequency stability over the past 24 hours. The line is almost perfectly flat, drifting by less than a part in 10 to the 15th. Another monitor shows the fountain's real-time status. A cycle counter, 93 out of 100 cycles complete. Morgan watches atoms being cooled, launched, detected. It's all happening inside a vacuum chamber in the next room, invisible, silent, but represented here as numbers and graphs. The work is routine. Almost boring. And that's exactly how it should be. In this field, boring means everything is working. Boring means reliable. Boring means the world's timekeeping infrastructure can depend on this lab's contributions. Morgan knows that somewhere out there, GPS satellites are broadcasting time signals partly based on this lab's clocks. Cell towers are synchronizing to those signals. Data centers are coordinating transactions. Power grids are balancing loads. But knowing that doesn't feel heavy or stressful. It feels like being part of something larger, a distributed system, a network of institutions and people all working together. No one person has to keep the world on time. No one lab. No one clock. It's a shared responsibility distributed globally. Around 10 p.m., Morgan does another round of checks. Still nominal. They eat a sandwich from a cooler bag, check email, read a technical paper about new techniques for laser cooling. Midnight approaches. The building is quiet. Most offices are dark. Security guard walks past on rounds, waves through the window. Outside, the city sleeps. Or at least parts of it do. Somewhere, people are checking their phones for the time, probably without thinking about where that time comes from, how it's maintained, who keeps the clocks running. That's okay. They don't need to know. That's what Morgan is here for. In our story, you can borrow Morgan's calm. Important things are being watched by people whose job is to watch them. Systems are running. Infrastructure is stable. My job for the next several hours is to rest. Even as cesium fountain clocks reached unprecedented accuracy, 1 second in hundreds of millions of years, physicists were already developing the next generation. The limitation of cesium clocks is fundamental. They use microwave radiation at about 9 gigahertz. That's 9 billion cycles per second. Sounds like a lot. But in physics, it's actually relatively low frequency. The precision with which you can measure a frequency is limited by how many cycles you can count. More cycles per second means finer resolution, like using a ruler with smaller markings. What if instead of using microwaves, you used visible light? Visible light oscillates at hundreds of trillions of times per second. Red light has a frequency of about 400 terahertz, 4 times 10 to the 14th hertz. That's about 40,000 times faster than cesium's microwave transition. In principle, an optical clock could be 40,000 times more precise than a microwave clock. But building such a clock is extraordinarily difficult. The challenges are immense. First, you need an atom or ion with an optical transition that's extremely narrow, meaning it responds only to a very precise frequency. Cesium's microwave transition is narrow. But most optical transitions in atoms are broad, easily perturbed by external fields, sensitive to collisions. Physicists searched for atoms with special transitions called forbidden transitions. In quantum mechanics, certain transitions between energy levels are allowed. They happen quickly. Others are forbidden. They happen very slowly. Forbidden transitions are actually ideal for clocks. Because they happen slowly, they have very narrow spectral lines. Several atoms turned out to have suitable forbidden transitions. Strontium has one at about 430 terahertz, red light. Ytterbium has one at around 518 terahertz, green light. Aluminum ions have one at around 1000 terahertz, ultraviolet. Mercury ions, calcium ions, indium ions, all candidates. Second challenge, you need an incredibly stable laser to probe the transition. Ordinary lasers, even good ones, drift in frequency far too much. Physicists developed ultra-stable lasers by locking them to high-finesse optical cavities, mirrors separated by precisely controlled distances. The laser frequency is locked to a resonance of the cavity. The cavity is isolated from vibrations, temperature changes, acoustic noise. These systems can achieve laser frequency stability at the level of 1 part in 10 to the 16th or better. Third challenge, you need to trap and cool the atoms. Ions can be held in electromagnetic traps called Paul traps or Penning traps. A single ion suspended in vacuum, cooled with lasers to its quantum ground state of motion. Neutral atoms can be held in optical lattices, standing waves of light that create periodic potential wells where atoms get trapped. Thousands of atoms can sit in these wells, each one isolated from its neighbors, all experiencing nearly identical conditions. The first optical clocks were demonstrated in the early 2000s. NIST built an aluminum ion clock, a single aluminum ion trapped in vacuum, interrogated with ultraviolet light. GILA, a joint institute of NIST and the University of Colorado, built a strontium lattice clock, thousands of strontium atoms trapped in an optical lattice. By the 2010s, optical clocks were surpassing cesium fountains in accuracy. In 2015, GILA's strontium clock achieved a fractional uncertainty of about 3 times 10 to the minus 18th. That's 3 parts in a quintillion. In practical terms, it would neither gain nor lose 1 second over the entire age of the universe, about 14 billion years. But that's almost meaningless as a practical statement because nothing can run for that long. What matters is what you can measure in the lab. With that level of accuracy, you can detect effects that were previously invisible. Einstein's general relativity predicts that time runs faster at higher altitudes, where gravity is weaker. The effect is tiny, about 1 part in 10 to the 16th per meter of height difference. Optical clocks are now sensitive enough to measure this. If you have 2 optical clocks and move one of them up by just a few centimeters, its ticking rate changes measurably. In 2010, NIST demonstrated this by comparing 2 aluminum-ion clocks separated by about 33 centimeters in height. The higher clock ran faster, exactly as relativity predicted. This opens new possibilities. You could use optical clocks to map Earth's gravitational field with exquisite precision. Differences in gravity correspond to differences in clock rates. You could monitor the flow of water underground, the motion of tectonic plates, the melting of glaciers, all by measuring tiny changes in gravity with portable optical clocks. You could test whether the fundamental constants of nature are truly constant. Most physicists think they are. But optical clocks are now precise enough to check. The fine structure constant, the ratio of electron mass to proton mass, the gravitational constant. If any of these changed over time, optical clocks comparing different atomic species would drift relative to each other. So far, no drift has been detected. The constants appear constant within measurement limits. In July 2025, NIST reported a new record. Their aluminum-ion optical clock achieved a systematic uncertainty of about 10 to the -19th. That's 19 decimal places of accuracy. It's 41% better than the previous record. It's about 10 times better than the best cesium fountain clocks. The rapid improvement in optical clocks has prompted discussions about redefining the second. Currently, the second is defined in terms of cesium. But if optical clocks are 10 or 100 times better, shouldn't the definition be updated to reflect that? Before that happens, several conditions must be met. First, optical clocks must demonstrate long-term reliability. It's not enough to set a record once. The clocks need to run stably for months or years. Second, different optical clocks around the world must agree with each other to within their stated uncertainties. A major international comparison was conducted in June 2025. Optical clocks in the US, Germany, France, the UK, Japan, and China were compared using fiber links and satellite links. The agreement was excellent. All clocks matched within about 1 part in 10 to the 18th. Third, there must be international consensus on which atom to use. strontium? Ytterbium? Aluminum? Or perhaps a definition based on multiple species? And fourth, practical issues must be resolved. Optical clocks are currently large, complex, expensive. They fill entire rooms with lasers and optics and vacuum systems. For a redefinition to be meaningful, the new standard should be reproducible in many labs, not just a few elite institutions. Work is underway to make optical clocks more compact and robust. Some researchers are developing portable optical clocks that could fit in a suitcase or a car. The goal is to make them practical for field use, for geodesy, for fundamental physics tests, for comparing clocks over long distances. The redefinition might happen around 2030 or 2034, according to current projections. It will be a historic moment, comparable to when the second was redefined in terms of cesium in 1967. But even if the definition changes, cesium fountain clocks won't disappear. They'll continue operating as secondary standards, as stable references, as checks on the optical clocks. Science builds on layers. Each generation of technology supports the next. You don't need to follow each advance, each record, each incremental improvement. It's enough to know that humans continue to ask, can we measure more precisely? Can we understand more deeply? And while they do that work, you're allowed to be wonderfully imprecise. Allowed to lose track of time. Allowed to rest without measuring how long you rest. Deep inside you, your body has its own clocks. Not cesium-based, not laser-cooled, not measured in gigahertz or parts per trillion. Biological clocks. In your brain, in a small cluster of neurons called the suprachiasmatic nucleus, sits your master circadian clock. It responds to light and darkness, organizing your daily rhythms. Cells throughout your body, in your liver, heart, kidneys, digestive system, keep their own time, cycling through patterns of activity and rest. Hormones rise and fall on schedules. Cortisol peaks in the morning, preparing you to wake. Melatonin rises at night, signaling sleep. Body temperature follows a daily cycle, lowest in early morning, highest in late afternoon. Sometimes these clocks feel misaligned. Too much screen light at night confuses the master clock. Blue wavelengths suppress melatonin. Jet lag throws them out of sync when you cross time zones faster than your biology can adjust. Shift work forces you to fight your natural rhythms. Stress disrupts the delicate choreography of hormones and neurotransmitters. You might feel tired at the wrong times, wired when you want to sleep, unable to sync with the world around you. But here's the important thing. Just as engineers can slowly steer a drifting clock back into alignment, your body can gradually resynchronize. And one of the most powerful tools for that reset is what you're doing right now. Sleep. While you sleep, your brain consolidates memories, sorting through the day's experiences. Some connections are strengthened, others pruned away. Metabolic waste is cleared from brain tissue, proteins and cellular debris that accumulate during waking hours. Immune function is boosted. Your body produces infection-fighting cells more effectively during sleep. Tissues repair. Growth hormone is released. Energy stores are replenished. You don't have to manage any of this consciously. You don't have to instruct your pituitary gland to release hormones or tell your glymphatic system to clear waste. You're not the chief engineer of your own biology. You're more like a passenger on a ship whose crew works below deck, unseen, maintaining systems you'll never directly observe. The best thing you can do is give them time, undisturbed hours where you don't interfere. So let's move through your body once more, releasing any remaining tension. Start with your face, your forehead. If there's any tightness from concentration, from thinking, from the day's worries, imagine it softening like wax warming. Give it 3 slow breaths to release. 1, 2, 3. Your eyes behind closed lids. They've been focusing all day, on screens, on text, on faces, on the world. Let them rest now, unfocused, drifting. Your jaw. Unclench if you're holding tension there. Let your teeth part slightly. Let your tongue rest in the middle of your mouth, not pressed against anything. Your neck holding up your head all day. Let the pillow bear more of that weight. Feel the muscles along your neck soften, lengthen. Your shoulders. So much tension accumulates here, from hunching over keyboards, from carrying bags, from stress that manifests physically. Imagine them sinking, becoming heavier, as if gravity has been doubled just for them. Let them drop away from your ears. Your arms from shoulders down to fingertips. Heavy, relaxed, supported. No need to hold or grasp or gesture. Just resting. Your chest expanding and contracting with each breath. You don't have to breathe deeply or control the rhythm. Just observe your body breathing itself. Your abdomen. Let it be soft, not held in or controlled. No decisions to make here. Your lower back, which has supported you all day. If you feel any discomfort, shift slightly until you find a more comfortable position. Your hips and pelvis making contact with the surface beneath you. Solid, grounded, supported. Your legs, thighs, knees, calves, ankles. They've carried your weight, propelled you through space. For the next several hours, they have no job to do. Your feet, the furthest points from your heart. Toes relaxed, heels resting, arches released. Scan through your entire body once more from head to toe. If you find any remaining tension, breathe into it gently and let it dissolve. Your body knows how to rest. You just need to stop interfering. While atomic clocks measure time with 19 decimal places of precision, you can let time become vague, unmeasured, irrelevant. You don't need to count the seconds until you fall asleep. You don't need to calculate how many hours of rest you'll get. Just be here. Breathing. Resting. Allowing. We began in a hallway with polished floors and framed photos of pendulum clocks. We passed through a heavy door into a laboratory where cesium atoms fly through vacuum chambers and lasers cool them to near absolute zero. We walked backward through time from sundials to quartz crystals, from Earth's rotation to quantum transitions oscillating billions of times per second. We saw how Louis Essen and Jack Parry built one of the first practical atomic clocks in 1955. How the second was redefined in 1967, moving timekeeping from astronomy into atomic physics. How cesium-beam clocks evolved into fountain clocks that toss atoms upward like water in a fountain, interrogating them for a full second as they rise and fall. How these clocks reached accuracies of 1 second in 300 million years, precise enough that if you'd started one when dinosaurs roamed the earth, it would be off by less than a second today. How hundreds of atomic clocks around the world are compared and combined to create International Atomic Time, which becomes the UTC time your phone displays. How GPS satellites, telecommunications networks, financial markets, power grids, and scientific research all depend on this invisible infrastructure of precise time. How optical clocks using visible light instead of microwaves are now 10 times more accurate than cesium, approaching 19 decimal places, sensitive enough to detect the gravitational time dilation from moving a clock up by a few centimeters. All of this extraordinary machinery, all of this collective human effort, all of this precision spanning laboratories across continents, exists for one purpose: so the world can share a common rhythm. So when someone says meet me at 3 p.m., you both know what that means. So satellites can broadcast navigation signals that help you find your way. so data can flow across networks without becoming hopelessly scrambled. So science can advance, measuring things that require nanosecond or picosecond precision. For you, in this moment, the point is the opposite. You do not have to keep perfect time. You do not have to measure your rest in seconds and minutes. You do not have to be as regular and predictable as a cesium transition. You're allowed to drift. If some part of you feels guilty about resting, as if every second not spent productively is wasted, remember this. Even the best atomic clocks spend most of their existence in a kind of quiet waiting. They sit in their temperature-controlled rooms, counting seconds that no one particularly needs at that moment. They're not asked to justify their existence or prove their value every hour. They're valuable precisely because they're reliable, stable, boring. Your sleep is the same. It may feel boring, uneventful, like nothing is happening. But that's its virtue. As you lie here, thoughts may still arise. Plans for tomorrow. Replays of today. Worries about next week. Notice them like clouds passing across the sky. You don't have to engage with them, solve them, or push them away. Just notice and let them pass like background noise around a very clear signal. Somewhere at this moment, an atomic clock is counting. Second after second after second. 9,192,631,770 cycles per second, never varying, never faltering. Somewhere, a technician like Morgan is checking readings, logging data, making sure everything remains stable. Somewhere, GPS satellites are broadcasting time signals. Somewhere, the BIPM is collecting data from labs around the world and computing TAI. You don't have to participate. You don't have to contribute. You don't have to pay attention. You can let go of the day's clocks, close your eyes if they're not already closed, and allow yourself to fall completely out of sync with schedules, obligations, and measurements. Fall into sync with your body's need for rest. If you wake later, whether in an hour or 5 hours, and realize you don't remember how this story ended, that will mean it worked. That will mean you drifted off somewhere in the middle, perhaps during the description of optical lattice clocks, or while thinking about GPS satellites, or during the body scan. And that's perfect. If on some other night you want another long, calm journey through the history of timekeeping, through precision measurement, through the quiet work of scientists and engineers maintaining the infrastructure we all depend on, you'll know where to find us. For now, the machines that redefine the second can continue their work. The cesium fountains at NIST and PTB and SYRTE and other labs around the world will keep tossing atoms upward, measuring their quantum transitions, contributing to the global consensus of what time means. You don't have to measure anything. You can just sleep. Sleep now. Good night.